Hey, good people. Arthur Morris here. I hope all is well. In this video, we're going to look at increasing and decreasing functions and the first derivative test. So to test for increasing and decreasing functions, if f is a function that's continuous on a closed interval and differentiable on an open interval, we know that if f prime of x is greater than 0 for all of x in the open interval, then f is increasing on the closed interval. If f prime of x is less than 0 for all of x in the open interval, then f is decreasing on the open interval, and f prime of x is equal to 0 for all of x, then f on the open interval, then f is constant on the closed interval. Okay, so if you need to write that down, you might want to pause the video right here and write theorem 3.5 down. Okay, so the guidelines for finding intervals on which a function is increasing or decreasing, number one, we locate the critical numbers of f on the open interval, and we use those numbers to determine test intervals. Number two, we determine the sign of f prime of x at least one test value in each of the intervals. And number three, we use theorem 3.5 to determine whether f is increasing or decreasing on each interval. So again, if you need to, I would advise you to pause the video here and write these guidelines down. All right, let's look at some examples. So here we're going to look at the graph first and see where it's increasing and decreasing, and then we're going to find the open intervals analytically. So this is in reference to the x-axis. So if we're looking at this graph going from left to right, we see that from negative infinity to negative 2, the function is increasing. And then from negative 2 to positive 2, the function is decreasing. And then from 2 to infinity, the function is increasing. Okay, so let's look at 7 graphically, and then we'll come back to number 5 and do it analytically. All right, so from negative infinity to negative 1, the function is increasing. And then from negative 1 to infinity, the function is decreasing. All right, so let's go back to number 5 and let's look at this analytically. So the first thing we want to do, I'm going to rewrite this function as 1/4 x to the third minus 3x. And then we want to find the first derivative so we can find our critical values. So 3/4 x squared minus 3. All right, and then after we find our critical values, we want to, or find the first derivative. We set the first derivative equal to 0 to find the critical values. So I'm going to multiply both sides by 4 to clear the fraction. So 3x squared minus 12 equals 0. Add 12 to both sides. Divide both sides by 3. And then the square root of both sides. So x equals positive negative 2. So positive and negative 2. So those are my critical values. All right, now after you find your critical values, you want to create a number line. And you want to put those critical values on your number line. And then you want to identify test values on each interval. So you're going from negative infinity to negative 2, negative 2 to 2, and 2 to infinity. So my test values, I'm going to let x equal, I'm going to test 4 in this first interval, then 0, or negative 4, sorry, and then 0, and then 4. I'm going to plug those into my first derivative and see if the value of my result is greater than 0 or less than 0. If the result is greater than 0 when I plug into the first derivative, then I know that the function is increasing on that interval. If it's less than 0, then I know that the function is decreasing on that particular interval. So let's find f prime of -4. So 3/4 times -4 squared minus 3. So -4 squared is 16, and 4 will go into 16 4 times. 4 times 3 is 12. So f prime of -4 is 9, which is greater than 0. And since that's greater than 0, then we know that on the interval from -infinity to -2, the function is increasing. Okay, what about f prime of 0? So we end up, for f prime of 0, we end up at -3, which is less than 0. So therefore, on the interval from -2 to 2, we know that the function is decreasing. And then finally, f prime of 4. Which gives us the same value as f prime of 4, which is +9, and it's greater than 0. So from 2 to infinity, we are increasing. Now, the first derivative test basically says that if I, on an interval, if I'm go from increasing to decreasing, then I have a relative maximum where that change occurs. So here, I'm going at -infinity, and you can look at the graph at that. I go from, I'm increasing, then when I get to -2 on the x-axis, it begins to decrease. So that tells me that I have a relative maximum at -2. And then the first derivative test says that, okay, if you go from decreasing to increasing, then you have a relative minimum at that point at critical value. So after I go from increasing to decreasing at +2, I begin to increase again. So it goes up, down, and then at -2, it increases again. And that tells me that at 2, I have a relative minimum. So when you change directions like that, you can determine your relative maximums and your relative minimums. Okay, so let's look at another problem here. All right, so here we have f of x equals 2x to the third plus 3x squared minus 12x. So let's first of all find the first derivative so we can find our critical values. So 6x squared plus 6x minus 12. All right, to find our critical values, let's set that first derivative equal to 0. All right, so I can divide both sides by 6. And then factors of -2, that equals +1. That'd be +2 and -1. Set each factor equal to 0 and solve. So my critical values are -2 and +1. All right, so now I'm going to make my number line so I can find where it's increasing and decreasing, where the function is increasing and decreasing using those critical values there. So I'm going to test -3, 0, and 2. Okay, so f prime of -3 so -3 squared is 9. 9 times 6 is 54. Minus 18 or plus -18 minus 12. So 54 or -18, -12, that gives us -30, or so let's just say minus 30. So f prime of -3 equals 24, which is greater than 0. So that tells me on the interval from -infinity to -2, I'm increasing. Okay, what about from the interval, on the interval of -2 to 1? We're going to test 0. So I'm going to come up a little bit so I'll have room to test out 2 as well. So if I test 0, then I find that I have -12, which is less than 0. Therefore, I'm decreasing on the interval from -2 to 1. Now, per the first derivative test, that also tells me that I have a relative maximum at -2, because I started increasing and then I got to -2 and turned around and started decreasing. So that tells me I have a relative maximum at -2. And then let's see here. All right, so let's test 2. So 2 squared is 4. 4 times 6 is 24. Plus 12 minus 12, so 0. Therefore, from 1 to infinity, I'm increasing. All right, so those are my intervals. Now, per the first derivative test, since I began increasing from -infinity and then I began decreasing at -2, that tells me that I have a relative maximum where x equals -2, and then after I began decreasing at -2, I continued to decrease until I got to where x was equal to 1, and then I began to increase again. So I was going down, down, down. So I was increasing, decreasing, increasing. I was going down, and I started back up. So it tells me I have a relative minimum where x equals 1. Now, if it needs the exact point, if it's asking for the ordered pair, then you need to take that 2, plug it back into your original -2, plug it back into your original function so you can find the y value that goes with it, and take the 1 and plug it back into the original function so you can find the y value that goes with it, the actual coordinate. So when you want the actual coordinate, you want to plug it back into the original function, not the derivative. Alrighty, let's look at one more problem. All right, so here we're just going to find these tests, find where it's increasing and decreasing. So first of all, let's introduce something new. The derivative of the absolute value of u is u over the absolute value of u times u prime. Okay. So derivative of 5 is 0, and then we have the -1 outside. We're going to leave it out there. Derivative of x, absolute value of x minus 5. In this case, u is equal to x minus 5. U prime is equal to 1. So the derivative of x minus, the absolute value of x minus 5 is x minus 5 over the absolute value of x minus 5 times u prime times the derivative of the inside, which is 1. Okay, so let's see here. So let's set this equal to 0 to find our critical value or values. All right, we're going to multiply both sides by, I want to make it positive, so negative absolute value of x minus 5. And that will leave us with x minus 5 equals 0 and x equals positive 5. All right, so we only have one critical value at 5. So I need to test the interval from negative infinity to 5 and from 5 to infinity. And you can test whatever value you choose. I'm going to test 0 and I'm going to test 6. All right, so we're going back to the first derivative to test those values. All right, so we have negative negative 5, and the absolute value of negative 5 is 5. So that gives us 5 over 5, or 1, which is greater than 0. Therefore, it's increasing from negative infinity to 5. The function is increasing. And then let's test f prime of 6. So we have negative, then 6 minus 5 over the absolute value of 6 minus 5. So at 6 minus 5 is 1, 6 minus 5 is 1, the absolute value of 1 is 1. We have negative 1 over 1. Which equals negative 1, which is less than 0. Therefore, from 5 to infinity, we are decreasing. So if we're increasing and then decreasing, that tells us that we have a relative maximum. We have a relative maximum at 5. And you're more than welcome to plug this into Desmos, that original function, and see how these functions are increasing and decreasing, because looking at these graphically helps out. All righty, good people, that's it for this video. Hope you found it to be helpful, and I will see you on the next one. Thank you.